Otherwise, you won't be able to answer the test 1 assessment. Okay? Okay. So I'm going to record this, inshallah. Right, Bismillahirrahmanirrahim. We are going into the second topic of chapter 2 on sampling distributions. Okay, so if you do have your statistics for engineers textbook, please refer to page 43 until 45. Okay, here we do have difference between two sample means. And what you need to achieve at the end of this topic is that you should be able to write down the sampling distribution of a difference between two sample means. Okay, last time we had only one single sample mean, X bar. Now you have two sample means. So we are not talking about individual two sample means, but we look into the difference, the difference between these two sample means. So you need to write down the sampling distribution of this difference between two sample means correctly. And you should also be able to calculate probabilities related to the difference between these two sample means if you sample from normal or from non-normal populations. Actually, you just extend what you learned previously. Okay? So the sampling distribution, okay, suppose you sample from X1. So last time you only had one X. Remember, X referred to population, okay, and then variable representing population data. All right. So now, suppose you have two populations, okay, X1 and X2, where both populations are normal. Okay, when they are normal, then it should click in your mind that the parameters characterizing these normal random variables will be the mean. So for population 1, you have mu1. Population 2, you have mu2. Okay, whereas the variance, okay, you need to know the variance as well. So the variance will be sigma squared, but this time we have two populations, then we put the subscript here just to differentiate between the two populations. So you have sigma 1 squared and sigma 2 squared. And when you do sample from these two populations which are normal, for any values of N1 and N2, N1 and N2 are two sample sizes. Any values, no constraint on N1 and N2. Can be small, can be large, can be either small or large, can be both large. Doesn't matter. Okay? So if that is the case, then what happened? The difference between sample means X bar 1 minus X bar 2 will also normal. Okay, will also be normally distributed. And what is the mean for the difference? So the mean for the difference will follow the position. If you are talking about X bar 1 minus X bar 2, then the mean will be mu1 minus mu2. Okay, as you know, mean measures the location, location. So it has to follow the pattern. So meaning if you have X bar 1 minus bar 2, then you have mu1 minus mu2 as the mean. But you can also have X bar 2 minus X bar 1. Okay, so in that case, the mean has to be mu2 minus mu1. Please take note, this is very important. Okay, 1 or 2, these are just generic. Okay, only notation. You can have your own definition, but as long as you have to, you are consistent in terms of the mean, that's fine. What about the variance? Regardless whether you have x1, x bar 1 minus x bar 2 or x bar 2 minus x bar 1, the variance of the difference will be the sum of variances. Okay, logically, if you think logically, the variance measure dispersion, yeah, variability. Dispersion variability can never be negative. That is, if you think logically. But mathematically, when you talk about variance of x bar 1 minus x bar 2, if you consider if you expand the variance, it will be like variance of x1 plus variance of negative x bar 2. And that negative, if you take out of the variance, will be squared. So that's why you have variance of x bar 1 plus variance of x bar 2. And variance for x bar 1 is simply sigma 1 squared over n1 plus sigma 2 squared over n2. Okay? So this distribution is actually available in the statistical table booklet. Okay, so you can have a look at your statistical table booklet just to remind yourself what is the distribution for this difference between two sample means. Okay. What about if you sample from non-normal populations? Okay, the same idea on the single sample mean. Okay, if you sample from non-normal distributions, then you do have to have this condition. The sample sizes are large. We don't focus on small sample sizes when we sample from non-normal populations. Then we can use the central limit theorem to approximate the distribution for x bar 1 and x bar 2 to normal. Okay, you can sample from binomial, you can sample from Poisson, from any other distribution. Even you don't have to know the population distribution. You can only know the mean for the population, the variance for the population. You don't have to know about the distribution for the population even. But as long as you have a large sample size for each, okay, for each sample, then the difference between two sample means will be approximately normal. Okay, and the mean for the difference will be the difference between the population means, and the variance of the difference of sample means will be the sum of variances. Okay, so please make sure. Okay, common mistake by students is that they put negative for this variance. Okay, so be careful. And another mistake students always do here on the location measure. So be consistent. If you're talking about x bar 1 minus x bar 2, then the mean has to be mu1 minus mu2. But if you talk about x bar 2 minus x bar 1, then it has to be mu2 minus mu1. Okay, any questions so far? Are you all clear?
No, no, madam. Okay.
Okay, so far so good. All right. So when we know that this difference of sample means is normal, then you can always approach uh, normality approach. Yeah, you can use normality approach to solve probabilities for this x bar 1 and x bar 2. But first you need to standardize. Okay, standardize. So this is the standardization. Again, you do have this formula in the statistical table booklet. Okay, uh, and we use exactly the same definition. The variable of interest this time is x bar 1 minus bar 2 minus its mean mu1 minus mu2. Okay, mu1 minus mu2 divided by its standard deviation, which is the square root of this variance, square root of the sum of individual sampling variances. Okay, you need to be very careful. Okay, if I can, let's see. So we know Z is normal with 0, mean and variance 1. Can I ask you, is this the same as sigma 1 over square root of n1 plus sigma 2 over square root of n2. What do you think? Is this the same?
Same.
Answer.
Same answer.
Huh? The same?
No.
Same.
No.
No.
Square root.
No, isn't it? Ah,
No.
you. Okay, this is not the same. Okay. And this is really a common mistake. It's okay, you do mistake now, but please do not do the same mistake later. Okay? This is not the same, guys. Okay? This is not the same. Okay, please be careful. Okay, the square root of this, so it's not the same as this. Okay? So to avoid making mistake, the same mistake, what you have to do is to simplify at this stage. Okay, you simplify first and then get the square root of that value, simplified value, just to avoid making mistake. Okay, right. So that is the standardization. So when you standardize, everything else will be just the same as what you did last time. Okay. All right, so let's look at what we have next. Practical examples. Okay, if you look at your textbook, you do have working examples, okay, with solutions. I'm not going to use the same example in here, okay. But what you have to do, if you refer to example 2.3, this is when you sample from normal population. Whereas example 2.4, you do have an example where you sample from non-normal populations. So what I want you to do is to identify how the distribution of the difference between two sample means is written. When you look at the steps, the step-by-step solution, look at how the distribution is written and recognize how the probability related to x bar 1 minus x bar 2 is solved step by step. And remember the book, okay, I highlighted this again. When you go to the solution, yes, the latest steps of the solution before you get the final answer. If you look at the book, really the book actually make use of the old statistical table, okay, where the probability available in the table is probability of z between 0 and a positive value of z. So don't worry about that. As long as you standardize x bar 1 minus x bar 2 to z, then use your calculator straight away. Okay, don't worry about whether to minus or to plus 0.5. That is when you make use of the old table. And really when the textbook was released, okay, by at that time the new table is not yet available. Okay, but anyway, as long as you get the same similar answer, that is okay. And another point, the answer that you get from calculator can be slightly different from the answer given by the book, because the book make use of z up to 2 decimal places. Okay, but if you have the z value more than 2 decimal places, okay, normally is you can have like more accurate z values, and then you get the probability value directly from your calculator, then there will be a little bit discrepancies. So that is fine. Okay, that is fine. Okay, so let's look at one task question from page 45. Okay, so we have this question here. A consumer of an electronics company is comparing the brightness of two different types of picture tubes in their TV sets. Okay, so you have two types. Type A has mean brightness of 100 and a standard deviation of 16. So you have information there from type A. And of course, the information you have here must be population information. When it is population information, then you should have Greek letters to represent this information. Why do I say population information? Okay, simply because the information does not refer to any particular sample. Okay, you need to be very clear on this. You are not referring to any particular sample. You only say type A has mean brightness of 100 and standard deviation of 16 without referring to any particular sample of type A. Okay, so 100 here is the mean, should be the mu value, mu A value. Okay, this is mu A value. Standard deviation of 16, this should be sigma A value. Okay, while type B has mean brightness of 110, so this should be mu B, and standard deviation of 14 should be sigma B. Now you take a sample. Okay, a random sample of 36 tubes from each type is selected. Okay, now you take sample, okay, of 36 tubes. Now, hold on a second. Do you see any distribution mentioned anywhere in this question? Okay, related to brightness, do you have any distribution stated? No, isn't it? No, you don't know what the distribution is, okay, for this question. But what you know is that the sample size is large. So the question, what is the probability that the difference between x bar B and x bar A is at least 8.5? Okay. So when you talk about finding probability of a random variable, then you have to know the distribution of this random variable. So how do you define the distribution for this random variable? Okay. So we need to look at the information again. We do have mu A, sigma A, mu B, and sigma B, right? And also we do have the sample sizes, which are both large. In that case, you should be able to make use of all this information to define the distribution for x bar B minus x bar A by using the central limit theorem. Okay, so you write down the information. You don't have to worry about the population of the population distribution because you don't know that. Okay, you are not given. You just need to write down the information given. Okay, and next, this is the fact. Yeah, the sample sizes are large. Therefore, you can define the probability distribution for x bar B minus bar A. This is a rephrase from the question. Okay. In this question, it's very clear that you want probability of x bar B minus x bar A being at least 8.5. Very clear. A little bit vague question, which is quite common. We will ask what is the probability that the difference between the sample mean B and the sampling mean A is at least 8.5. So in that case, it could be challenging for some students to rewrite or rephrase that sentence into this mathematical expression. Okay. But anyway, this is what you want to find. So you need to define the distribution first. So we can use the CLT, central limit theorem. By central limit theorem, the distribution will be normal. Okay, although you don't know the population distribution, that's fine because your sample sizes are large. So you can approximate the distribution for x bar B minus x bar A. Okay, when that is normal. So be careful again with the mean here. You have to start with 110 because you have x bar B first. Okay, minus 100. And the variance of the difference has to be the sum of the variances. Okay, so don't forget to square sigma A and also sigma b. So this is directly from the information available, and I would advise you to simplify these values. Okay, to simplify. Okay, some students they will get values in decimal places even. Alright. So once you get this distribution, then it's easy for you to standardize when you solve the problem. Okay. So this is the distribution just now, and this is what you want to find. Okay. What you have to do, although you don't know the distribution of the population, that's fine, and you don't even have to worry about the continuity correction factor. We will do that in the next topic. Okay. So straight away, standardize x bar b minus bar a to z, and the value of a difference should be standardized as well. So you have x 8.5 minus its mean 10 divided by its standard deviation, square root of this 113 over 9. Okay, so this is coming back to chapter 1. Nothing is new at this point. Okay, you just need to simplify further and use your calculator to get the answer. Okay, if you round the value of z here to 2 decimal places, you will get the answer exactly the same as what the book give you. Okay, but if you do use your calculator directly, okay, then you will get this answer 0.6640. So that's why I said there could be a slight discrepancy if you use z to 2 decimal places or z to 4 decimal places like this. Okay, but doesn't matter, both values or both answers are acceptable. Any questions so far, guys?
Doctor,
Yep.
how do you know this is a normal distribution?
Very good question, Marzuki. I mentioned to you just now, okay? You sample from
So,
unknown population, right? You sample from unknown distribution. Correct me or not? Am I correct? You
Yes.
sample from non-normal distribution. Let me go back. Oh dear. Okay, here. You sample from any distribution. You don't know what population you have, right? Yes. But now look at this sample size, 36. It's large, isn't it?
entity,
Hmm?
large entity, large
See, the sample sizes for both sample are large. So what does the sample limit theorem say?
x1 and x2 must be
X bar B or X bar A, in this case, will be normal, isn't it?
x bar b.
X bar A and X bar B both will be normal. Correct me. Yes or no?
Yes.
Okay, remember when you learn chapter 1 last time, chapter 1 pula, in the first topic of this chapter, you should have watched the video. Okay, when you deal with single sample mean, X bar alone. Okay, when you sample from normal distribution, then X bar will be normal. But when you sample from non-normal, any distribution, then X bar will also be normal as long as the sample size is large. You get me or not?
Oh, I get it.
Okay, so now if X bar A and X bar B are individually normal, so thus the difference between them will also be normal.
So the
Then
key
follow.
is 36. It's
Pardon?
random. So the keyword is random
The sample
sample.
size.
Oh,
Yes. When you sample from any distribution, you don't know what distribution you have here. In this question, no distribution is mentioned. But you look at the sample size, it's large.
so what
Uh,
if the random sample is small?
that's what I said again. If you sample from non-normal distribution and the sample size is small, we don't cover that in the course.
Okay, okay, okay. Alright.
Many times I already talked about this. Okay. For the case where you don't know what distribution you have, okay, we don't cover the case where sample size is small
Oh,
because it tends to follow the parent population. So we don't cover that in this course. If we sample from any other distribution other than normal, always the sample size will be large so that we can use the normality approach.
okay, understand.
Okay, very good, Marzuki. Okay, so you can go through this solution again and you have to be clear on the basic, okay? Otherwise, you keep on asking, why is this, why is that? And then you don't move on. So now you know why is normal because although you sample from any other distribution, but the sample sizes are large, so you can use normality approach. Okay, you can assume normality for x bar b minus bar a, and then you can solve the probability problem for this particular random variable. And then you just standardize as usual, as you did in chapter 1. Okay, so you get this, right? So let's look at, before we leave, not leave for this class, leave for the for the topic, okay? Before we have a break. We have another example here, okay? So this is sampling from Poisson, okay? Poisson distributions. Again, Poisson is not normal. So you need to look for the sample size. Yes, the first one is 32, and the second one is, oh, the first one is 30, isn't it? So you have 30, the first. Okay, the first sample size is 30 and the second sample size is 32, right? Where, of course, mean for Poisson here, you need to know for Poisson, this is the parameter that define Poisson distribution. So the first mu is 54 and the second one is 58. So how are you going to get the probability of x bar 1 minus bar 2 from 0.5 to 2? Again, use the fact that you sample from non-normal distribution and the sample sizes are large, then the difference between these two sample means will be normal as well. Okay, so you sample from Poisson populations with those parameters. Okay, so you need to define the distribution for x bar 1 minus x bar 2. All right, so this is what we want. So define the distribution first. What is the distribution for x bar 1, guys? X bar 1 alone.
Normal.
Normal with, what is the mean for x bar 1?
54.
54.
Oh,
The variance?
54 also.
54.
54
The variance.
over
Uh,
30.
Oh, with 30. That's great, Afiq. Thank you. So you have x bar 1 is normal with mean 54 and variance 54 over 30. Similarly, for x bar 2, it will also be normal with mean 58 and variance 58 over 32. Isn't it? 32. Okay? Now, but we don't want to use individual x bar. We want x bar 1 minus x bar 2. Okay? So, then you have to define the distribution for x bar 1 minus x bar 2, which is normal also Okay, individually they are normal, then the difference will also be normal. With mu, look at how you write. It has to be mu1 minus mu2. Mu1 minus mu2. Because the position, yeah? It cannot be 58 minus 54, although 58 is larger than 54. You have to follow this pattern. Okay? And the variance has to be always the sum of variances. Okay? Don't square 54 and 58, please. Because you know these are lambdas. And lambda is actually the mean and also the variance for Poisson. So be careful with that. And as I mentioned last time, to avoid making mistake, you can simplify these values first. Okay. So is it possible to have a mean negative? Guys? Is it possible? No. Is it possible to have a mean negative here? Yes or no?
Yes, madam. Possible.
Possible, isn't it? Possible, because this is location measure. Okay, and you're talking about the difference. So when you say negative, it means potentially x bar 1 can be smaller than x bar 2. That's why you get negative value for the mean. Okay? But you can never have negative variance, please. Okay? That will be very wrong. So again, I would use this further simplified values, okay? Because then life will be much easier lah when you want to standardize later. So you still haven't finished with this, okay? What you need to do is to standardize, yeah, x bar 1 and x bar 2. And remember, when you standardize, it has to be the value first, 0.5 minus mean, which is negative 4. Sometimes students forget that negative. Okay? So this is mathematics. Negative 4 is not the same as 4. Okay, so please be careful when you write down the values. Divided by the square root of the variance. Okay, we already simplified this variance. Okay, so that's why I said you simplify first so that you can use the value easily. And once you get to Z, I believe you are familiar with this already. Use your calculator. If you round the value of Z to 2 decimal places, then you tend to get the same answer given by the book. But if you use your calculator straight away, you get slightly different value. Okay, only a difference of 0.0001 in this case. Okay, so any of these two values are acceptable. Okay, so no worry about that. Okay, so can you wait for a while? I want to just finish a little bit on this. Can you? 5 minutes.
Yeah.
Okay. Now, when we talk about a difference, you tend to get this kind of problem. If I say, for example, suppose we have this kind of question. Okay, what is the probability that the difference between sample means 1 and 2 is less than 3? What about the next question? What is the probability that the difference between the sample means is less than 3? Do you think there is any difference in the two questions? Are they the same? They are not the same, guys. Okay, although at times you can have the same answer, but not necessarily every time. Okay, so here you need to think about which one to use the modulus. Okay, so for the first one, you can see here the difference that we are talking about has a specific order. Specific order. You want a difference between sample 1 and 2. So it has to be x bar 1 minus x bar 2. Or if I say between sample 2 and 1, then you have x bar 2 minus x bar 1. Okay. However, for the second one, we don't have any specific order. Okay. So for the first one, it means this one. Okay. What is the probability that x bar 1 minus x bar 2 is less than 3? This is representing that phrase. Okay. Alternative way of writing the question. But for the second one here, you don't have any specific order. Maybe you think this is x bar 1 minus x bar 2. Or it could be x bar 2 minus x bar 1, right? So which one then? So for the second one, you should use modulus. Okay, modulus. Now the next question. How are you going to expand the modulus? Because you cannot solve unless you solve the modulus first. You need to expand the modulus. Okay. So generally, if you have modulus of x bar 1 minus x bar 2 less than or equal to, or sometimes you can have less than, doesn't matter. Okay. So what does it mean? It means that x bar 1 minus x bar 2 is from negative d to d. And d can be any value. Okay, d can be any difference value. Okay, so you're talking about so if you have this negative d and d, okay, so you're talking about this area. This area from d to from negative d to d. So once you after you expand, then only you standardize. You standardize. So negative d minus the mean for x bar 1 minus x bar 2 divided by the standard deviation of x bar 1 minus x bar 2. Okay, this is just notation, okay? You just get the mean for x bar 1 minus x bar 2 and the standard deviation. You standardize as usual. Whereas the second value is d minus the mean of the difference divided by the standard deviation of the difference. Okay? Whereas for probability of a modulus of x bar 1 minus x bar 2 being at least d or greater than d, then this is the way you expand. It has to be first without the modulus greater than or equals to d, and it has to be plus. Okay, plus probability of x bar 1 minus x bar 2 less than or equals to negative d. So this is basically if this is negative d and this is d, you're talking about the tail area and the tail areas. So you're talking about this area here. Okay. So you have above d plus below negative d. Then only you can expand or standardize. Okay, standardize. The difference becomes z. The value of the difference becomes the value of z by taking off the mu of a difference from d divided by its standard deviation. And similarly for the second value also, you standardize negative d minus the mu, the mean for the difference divided by the standard deviation of the difference. And once you get to z, everything just like what you did. in chapter 1. Okay, so just be careful with the statement. So if you revisit this question, if I say, instead of asking about what is the probability that probability of XA or X bar B minus X bar A is at least 8.5, now I put it in sentence like this. What is the probability that the difference between the sample means? How do you know? Is it between X bar A and X bar B, or is it between X bar B and X bar A? Is it X bar A minus X bar B, or is it X bar B minus X bar A? Which one? Okay, so you can try this out. You don't have any specific order for this particular question, so you have to deal with modulus. Okay, so you can either use this one, so you need to expand later, or if you want to use this one is also okay. Modulus of X bar A minus X bar B. But of course, the distribution has to be normal with mu A minus mu B. Okay. What happened? These two approaches will lead to the same answer. It is almost the same as what you get just now. Okay. However, if you don't put modulus, okay, you will get wrong answer for the second one. When you don't put modulus, the answers are not the same. Okay. Without the modulus, probability of X bar A minus X bar B at least 8.5 will be 0. So that's why you need to be very careful. Okay. For a question like this, no specific order, you have to put modulus. So if you put modulus, either you use the first choice or the second choice, it will give you exactly the same answer. Okay, so you expand first and then solve, or standardize and solve, you get this answer. Okay, but if you don't use modulus and approach the second one, you get wrong answer. Okay, so you can try this out, and we could have many questions like this. So please make sure you know when to use modulus, when you don't have to use modulus. No specific order, use modulus. If you have a specific order of a difference between S bar 1 and S bar 2, for example. So in that case, no modulus. Okay. So we finished this topic. In particular, hopefully you should be able to write down the distribution of a difference and use that distribution to solve probabilities related to the variable that represent the difference between two sample means. Okay, guys. So I believe this is the end of second topic. Okay. So we'll stop for a while. Okay, we stop for a while, about 10 minutes before we continue with proportion. Right?
Okay.
Okay, so Nazrul asks, is this like a book, pages 44, example 2.3? Yes. Okay, you look at table. Actually, I think that class, isn't it? 2.3, 2.3. Yes, yes. So, but 2.3 is very clear-cut question, Nazrul. Okay, for question, for example, 2.3, very clear-cut question. But number 3, yes, you have modulus, right? No, number 3 for example 2.3. You do have modulus, so you can have a look at that. Okay, Nazrul. Okay, guys, I see you in 10 minutes time, inshallah.